There's a few things I want to do today. First, I sort of want to pick up from where we were last class, and I want to clarify some things. So it became apparent in the breakout groups that perhaps I had not defined these classifications of voxels well enough. So, as I mentioned earlier today in an email I sent out before this class, I've updated the site file to contain this new classification system here, as well as this block orientation compass, which we'll get to later this class. So, I just want to go back through these very quickly so that we're all sure what each classification means moving forward, and that it doesn't leave you with any sort of open-ended questions as to what you're going to look for. So in this classification legend I have right here, essentially what I've done is the voxel in question is shown in red, and the context voxels, I'd say the minimum context voxels, are shown in gray. And what I mean by the minimum context voxels is that I just have voxels applicable voxels on each side of the voxel in question. So for example, in the interior roof, where what is going on is that we have no exterior faces on the sides, but we have an exposed roof. The floor is not exposed. You can see on this demonstration legend right here, we have the top exposed, just like this roof is exposed, and the other 5 sides, so the 4 vertical faces and the horizontal bottom face, are all covered. So even though in this legend it shows these 4 gray neighbors, we can call them, corresponding to the or 5 gray neighbors corresponding to the 5 covered faces of the interior roof voxel classification, it could also be something like this in real life. You know, there can be more things in the corners, there can be, you know, more voxels around, like so. But, you know, you can extend this context out, into infinity. So that's why I've just shown the bare minimum neighbors for a given condition. The other thing I've done is I've tightened up the naming conventions a little bit. So this will be pretty much the same as last class, with the exception that in this column that I changed the side face label to just side, so it's one word. And instead of having, a condition where it's just column, I've changed that kind of non-descriptive version of the voxel condition from having no description when it's between 2 vertical neighbors to sandwich, just because if you look at, for instance, the column sandwich condition, I think that this kind of looks like a sandwich. So that's what we have. We have this matrix that's composed in the y-axis of interior, column, tunnel, corner, side, and nubs. These are sort of designating the conditions of the side faces. And in the x-axis of this matrix, we have roof, sandwich, bottom, and floater, which are the designations for the vertical, or the top and bottom of the voxel in question. So I'm going to quickly go through the classifications just so it's very clear. When we're talking about this classification system, an interior voxel is 1. So again, the y-axis here is referring to the sides. An interior voxel is one that that is completely covered in the sides. So you can see, for example, this first one has no neighbors in the side. The second one has no neighbors to the sides. The third one has no neighbors to the side. The interior roof, the roof condition is something that has an exposed top face. So it's a roof, it's exposed. An interior sandwich is something that has no faces exposed. So interior specifies that it has no side faces exposed. The sandwich condition signifies that it doesn't have either its top or bottom face exposed. And then finally, the interior bottom specifies that it has just its bottom face exposed. So if you see in this legend right here, all side faces are covered. That's what an interior condition is. And the top face is covered, so with only the bottom exposed, we call this an interior bottom condition. There is no such thing as an interior floater, because what that would mean is that there would be neighbors all around, but the top and bottom would be exposed. Actually, maybe there is an interior floater. I'll add that to the list. For some reason that one escaped me, so that's why classification systems are great. So that is the interior floater. I don't know if this condition will ever come up, but there it is. Column describes a condition where a voxel has no neighbors surrounding its side faces. So you can see that, for instance, a column roof, in the legend here, none of the side faces are exposed. The roof is exposed, hence the roof condition, and the bottom is covered. So you can think about this as the top of a column. A column sandwich is one where, of course, all the side faces are exposed, but since it's a sandwich condition, both the top and bottom faces are covered. A column bottom is one where all side faces are exposed, the bottom face is exposed, but the top is covered. And a column floater is another special condition where no faces are covered. And essentially what that would relate to is a voxel like this, where you have a little, UFO floating out in space. So that is a column floater condition. Of course, in real life, that doesn't make much sense, but in this class, if you can sort of model it in an interesting way, sure, why not? We have a tunnel. A tunnel is something, I've just called it a tunnel. You could also think of it as a bridge. It's just a condition where two side faces are exposed, so it's connecting two ends. So you can see right here, this is a tunnel roof because it has two side faces exposed, the bottom is covered, and the roof is exposed as well. We have a tunnel sandwich, so you can see this is what a tunnel sandwich looks like. It just has two side faces exposed. We have a tunnel bottom, like so. A tunnel floater. We have a corner condition where essentially two side faces that are adjacent to each other are exposed. So a tunnel has two opposite side faces exposed. A corner condition has two adjacent side faces exposed. And again, they intersect with the x-axis in the same way. So a roof condition specifies an exposed top. A sandwich condition specifies a covered top and bottom. A bottom condition specifies an exposed bottom. And a floater condition specifies an exposed top and bottom. Finally, the nubs condition is one where only one side is covered. So I called it a nub because it's like a little, nub that sticks out. And the same interactions occur. So a nubs roof is one with the roof exposed. Nub sandwich has top and bottom covered. A nubs bottom is one that has the bottom exposed. And a nubs floater is one that has both the top and bottom exposed. I've set up the layers in the file to correspond with these, and these are the same as the last class's file, except I've just renamed them. So I've appended the sandwich descriptor and changed the side face just to side to sort of make it a little bit tighter. So does anyone have any questions about this classification system? Or any of these not clear? Okay. Great. So if that's the case, we can move into the grasshopper file. And the grasshopper file also continues where we left off. Continues from where we left off. Oh, Colin, is it assumed they are all above ground level? No, it's not assumed. These classifications have no relation to a certain elevation. They could be below ground, they could be above ground. The only classification is the relation of the particular voxel in relation to its direct neighbors. So, for example, you could have a floater which is buried 1,000 feet below ground. We're not sure of the context. So let's open Grasshopper. And in today's class file, there will be a new Grasshopper file. And this is going to be very similar to the one we had last class, except what I've done is, again, I've kind of cleaned it up. So just to review, the first part of this giant definition, this is what we did 2 classes ago now. So we essentially looked at this pile of voxels, and we found the center points of all of these faces. So for all 6 faces of each voxel, we found the center point, and then what we did was we said, okay, for a given voxel, so there's a, an axonometric voxel with its center faces, compare it to all the other faces that it might share. So for instance, if there was another voxel there, we could say that this side face shares, or the point at the center of this side face shares a position with a point at the center of this voxel's side face. So therefore, that would be a covered face. So we did that sort of logical test by looking at the distance between those points, seeing if it was smaller than a very small number. So you can see here it's a small number, which is 0.0001. And from that, we created a Boolean. So essentially, a list of 6 trues or falses that correspond to north, east, southwest, top, and bottom. And from there, we use those patterns of trues and false to call or remove the faces in this north, east, southwest, top, bottom list that are covered. So what's coming out of this call pattern is essentially a list of all the exposed faces. So a list of exposed faces. That's what we're getting out of here. From there, what we did last class is we went and we found all these conditions, and we did this as a group, or rather I sort of showed a few different examples. I showed you how to do an interior roof, I showed you how to do a corner roof, and I showed you how to do a corner floater. What I'm going to do now is I'm going to do 2 more examples here, just so we can sort of go through this again. But then from there, what I'm going to do is, now that we've classified these boxes, we need to realize that there's a directionality to them, right? So what I mean when I say they have a certain directionality is that, for example, let's find a good condition here. So, for example, we have a nubs piece right there, right? But we also have a nubs piece right there. Both of these pieces are nubs pieces. However, this nubs piece right there, and I'm aware of my arrow offset, this nubs piece right here has 1, 2, 3 exposed faces, which are, facing generally in this direction, this direction, this direction. This nubs piece here has 3 exposed faces, but they're facing in different directions. It looks like this nubs piece is rotated 90 degrees, we could say counterclockwise in this image, from this nubs piece here. So before we can start taking our kind of detailed geometry, so here's my nubs piece right here. It's this kind of weird nub with T guardrails and Tom Nook gargoyles. Before we can take this kind of sophisticated geometry and assign it to these conditions, we need to do one more step of further classification and figure out the rotation of these voxels in relation to our local coordinate system. So that's what we're going to do after this. I'm going to do 2 more examples of classifying these voxels. One is going to be that interior floater, which for some reason I just realized existed at the beginning of this class, and the other one's going to be one of the class's choice. So after that, we'll do the rotation classification, and then after that, I'll show you how to start inserting your sophisticated geometry into your pile of voxels. So by the end of this class, what you will be able to do is you'll be able to take sophisticated geometry that maybe you spend the weekend and Monday designing, and you'll be able to populate this tower of blocks. So I'm going to do the interior floater condition, the classification, just because it wasn't listed last class. What I'm going to do is I'm going to save this file right here. So I'm going to save the assignment site file in Dropbox just to make sure we have that one last condition recorded. And then what I'm going to do is I'm going to do one more example here. That's the interior floater. I'll save it. But could, a few people in the chat let me know what second example you want me to do? Like, was there one of these conditions, be it a nubs bottom, a side bottom, a corner sandwich, a tunnel sandwich? Out of all these conditions, maybe list 1 or 2, maybe I'll get to a couple, to sort of take you through if the groups were unable to solve it. But I'll start with figuring out a floater condition. So to solve a floater condition, what I'd do is I would just take my interior roof condition. So remember, we are working with these kind of building blocks, as it were. We have a test to find a letter, and we have a test to compare the list of, or the length of the list of letters, so the northeast, southwest, top, bottom. And we can use these 2 sort of tests in conjunction to sort of parse out different scenarios, so different voxel classifications. So what I'd do to find the interior floater is I'd just start by copying the interior roof. Oh, and one thing I should mention, and I'll show you how to do this. What I've done here is, before I continue, is I've created all of these custom components that allows you to essentially find, for example, the column floaters. So let's plug in something. So what you can do with these kind of small little custom components is you can just plug in your text. So for example, we can go to our call pattern out, so our list of exposed faces. We can just plug that into, for example, the column floater text in, and then what should happen is you get the properly selected voxel, right? So I've made all these placeholder components for you to use to reference. However, for your assignment 3, and I'll make this explicit in the assignment sheet that's handed out on Monday, you can use these if you really can't solve something, but you will lose marks for it. So essentially, I don't want you to get caught up in doing this. There's lots of things to do in this course. However, if you do decide to use these components rather than figuring out for yourself or in the group like we did last Monday, you won't be graded as highly. So these things are here for you to reference, but if you can, don't rely on them. But it seems like most of you are figuring out most of these anyways. So we're working on the interior floater right here. So I'll just change its label to interior floater. Again, if we're thinking about the exposed faces, a floater has an exposed top and an exposed bottom. So simply what I could do is I could just copy, I'd ungroup all this. I would just copy this testing for a letter section. I would zoom in to add another and into my gate and. So remember, this is a sort of a way to combine certain logical statements. I would plug this second test into the the newly created gate and input, and I would just change my letter to find to be B. So now we're looking for a condition where both the top is exposed, so the top, the bottom is exposed, the bottom of this voxel right there. And then finally, if we know both the top and the bottom are exposed, we know that there's going to be two faces. I'll click OK. And now if I look in my pile of voxels, you can see there are indeed some interior floater conditions. So that's an interior floater right there. So what I'm going to do is I'm just going to save this, and now if you reopen this Grasshopper file, you'll have the interior floater classification as well. I want to do one more example. Which of these classifications was one group or multiple groups unable to figure out? I know you guys didn't figure them all out. So was there any one in particular that seemed kind of tough that you would like me to go through?
There's a couple folks in the chat asking for tunnels.
Yep, that's perfect. That's great. So I will do a tunnel. So a tunnel, why don't we do a tunnel sandwich? So a tunnel sandwich, if we look at it, so when you're moving through all of these, you can go to the classification and see what's required. So in this case, a tunnel sandwich, I'm just going to zoom on this one right here, is one that has two opposite sides exposed. Oh, and Homa, is the Boolean inverted for the interior floater? No, it's not. It's not inverted for either the top or the bottom because we're testing for the presence of both. So is the top exposed? Is the bottom exposed? So for the tunnel floater, we can start by just, or for the tunnel sandwich, sorry, we can just start by copying our standard kind of kit of parts here. So I'll just copy from the interior floater, which I last did. So I can just go Control C, Control V. And I can delete this interior floater label because I already have a tunnel floater. If I want to, I can take a look at the this list that's already there, or this component that's already there. So what I could do, oh sorry, and I said I'd do a tunnel sandwich. I'll do a tunnel floater instead. What I could do is I could take the input text plug into the text in the custom component, and then I could look at the pile of voxels just to see how many there are. So you can see here, if I'm doing a tunnel floater, there are a couple tunnel floaters. So that's how these kind of custom ready-made components work. I'll show you how to package a component like this once I'm done doing the tunnel floater. So you could do this. This is kind of like a preview. So what we can do is we can start thinking about what sides are exposed. So a tunnel floater is this one here. So does anyone want to guess how we might, outside of Grasshopper talk, just ask a computer or ask someone how you would describe a tunnel floater? So what could you say about the sides that describes this voxel here? Yeah, Jeremy?
Can you test top and bottom, and then say test for east and west, or north and south?
Yes, that's perfect. So Jeremy said test for east and west, and then the operative word here is or north and south, as well as top and bottom. So since we know top and bottom, I already have top and bottom plugged in. The Boolean is not inverted, so that's testing for a presence of top, a presence for bottom. So you want to test for the top, you want to test for the bottom, that's good. Now let's start testing for the side. So since we know we want to test for east and west, let's start with that one. Since there's two directions, east and west, let's just copy both the top and bottom tests here because we need two. So Control C, Control V. Now we're going to test for east and west. So what we can do is we can first change this T to be an E. So caps locks, E. Remember in our match text, we turned off caps or case sensitivity. So even if you don't use uppercase E, it's fine. But it's kind of looks cleaner that way. So east, the second one we want to test is west. So I type in W. So now it's giving us a bunch of trues and falses as if east or west is exposed. We want to say east and west. So what we'd do is we'd go to math, operators, gate and. So that is math, operators, gate and. And we would plug the east output, so all these trues and falses from east, and then the west output, all the trues and falses from west, into the gate and. So is east present and is west present? So as Jeremy said, we need to test is the east present and west present, or is north and south present. So what we can do now is we can just copy these two as well as the gate and we just made. Go Control C, Control V. And now instead of east and west, we're going to go north and south. So north, okay. South, okay. So is north present and is south present? The final step here is the or. So is east and west present, or is north and south present? So to grab the or, we can go to maths, operators, gate or, and we can plug the east and west and result into the A input of gate or, and the north and south and gate result into the B input of gate or as well. So this will sort of combine them and we'll say one or the other. Once that's done, we're already testing for the top and the bottom. Yeah, Jeremy. Or Nora.
I was just wondering if we should use XOR in this case, if it's a tunnel.
You could. I mean, there's many different ways to sort of kind of approach these problems. So for instance, we're being extremely explicit in this. So we're going top and bottom, and then the next step we're going to do is we're going to test for how many different sides. So 1, 2, 3, 4. You could be a lot less explicit about this. So you could figure out different ways to, satisfy this constraint. And if you can find a way that's more, efficient, I'd say go for it.
Yeah, I see.
Yeah, so Zora here, it says Boolean exclusive disjunction. So it's essentially talking about a not or, so a negative or. So you could use this in conjunction with a top and bottom test, for instance. So, I mean, there's lots of different ways to do these. So we can plug the gate or into, I'll just plug into the third one. So now I have top and bottom, and then east and west, or north and south plugged into the final gate and. So let's see. Wenting.
Hi, you can hear me now, right?
Yeah.
Just a question about the top and bottom. So in this case,
Yeah.
the top and bottom you're using Boolean is all true, right?
Top and bottom.
Bottom, the Boolean is all true. Because do you need to? Because I think we need to choose the true or false for the top and the bottom. Is that right?
True.
To convert the Boolean or not invert the Boolean.
Oh, yeah. So the Boolean is not inverted because this tests for exposed faces. So when the Boolean is not inverted, it's asking, is a top exposed face present? And then...
Okay.
Yeah.
So if so just repeating that, it's if that is exposed, it's Boolean, doesn't need to be invert.
Correct.
Okay, thanks.
Yep, no problem. So yeah, so what we have here, just to quickly recap, is we have, maybe I can draw on this, we have top. So is there a top? And that's going into this gate and. We have a bottom. So is there a bottom? And that's going into this gate and. And then finally here we have that east and west, which is going into the or. The north and south, which is going into the or. And that or is going into the and. So essentially, this is what we built so far. But when you think about this, it might be the case that in this case, a tunnel floater is the only, voxel configuration that satisfies all these conditions. But I'm, not sure. There might also be a corner condition that satisfies these conditions. Maybe, maybe not. So you can add one kind of extra layer of certainty, and what you can do is you can go down to your testing for a list length, group. So this is the group, if you remember, we're just simply measuring how many exposed faces there are. And then we're just asking, is the length of the exposed faces, in this case 4. So if we look at our tunnel floater, there's mouse offset. So there's 1, 2, 3, 4 exposed faces. So what we can do is we can put in a 4 here. So we want to test that there's 4 exposed faces. And then we can plug this list length into our final gate and. So the final gate and that goes into the call pattern. So to add one more input, we can press the little addition icon there. So zoom into the gate and press the little addition icon. And now you can take these trues and false, plug it in. And that should be that. And when I look at the call pattern now, so I select the call pattern, I'll look at my pile of voxels, and you can see that the you can see that the selected voxels are indeed tunnel floaters. So that one's floating. There's a tunnel floater. You can see it's floating. And then there's another tunnel floater right there that's floating. So does anyone have any questions? So I mean, to elaborate on Nicholas's answer there, so the mass addition, it just sums all numbers. So if you have, you know, a 111 going into a mass addition, it's going to give you a 3. In this case, what's happening is we have a true and a false going in, right? So essentially, it's this kind of interesting thing where okay, so let's here, I'll quickly review this because that's a good question, maybe kind of a hard one to get right away. So essentially what we have coming in, I'll just grab the input text. Okay, so let's look at this list. So essentially what's happening is we have a list coming in. So we have a north, and east, a south, a west, and a bottom. We're asking to find this letter. So we're saying, is there an S in this list? And what the match text component is giving us is it's comparing this letter to each letter in a list, and then it's giving us a false, false, true, false, false. So S is not N, false. S is not E, false. S is S, so it's a true. S is not W, S is not B, so we get a false and a false. What the mass addition is doing here is it's adding up all these trues and falses. Now that might sound counterintuitive, but if you remember in, you know, binary, a false is a 0, a true is a 1. So if, for example, we plug these lists of trues and falses into an integer component, what we'll get out of here is a bunch of zeros and ones. So what we're doing here is now, if you think about it, if we're adding up all these zeros and ones, so what mass addition does is it adds up all these values in a list. The answer here would be 1. The answer here would be 1. The answer here would be 0. And what we can do is we can convert that. So if you look here, we have a 1, a 0, a 1. We can convert this back to a Boolean, because again, ones and zeros and trues and falses are interchangeable. Essentially what we get out the other side is, again, a list of trues and falses. So what this is doing is it's, rather than giving us a, you know, a true or a false for each individual item in the list, we're essentially adding up all the trues and falses. And if there's at least one true in a list, or in this case, if there's at least one S in a list, then it will give us a value that's at least 1, not 0, and it'll give us a true. So we're saying true, there is at least one item, one S in that list. So that's what we're using the mass addition for here. It's kind of an off-label prescription, I guess, but it works quite well. I think I saw another hand, but it has disappeared. So if anyone else has a question, feel free to ask. What I'm going to do is I want to show you how to package components. And what I mean by package is this custom component here. So the tunnel floater custom component that I left in this class document, it's not a custom scripted component. It's a cluster of components that I've sort of just packaged up. In this case, it has a password on, and that's how I know if you did the work or not. So But what you can do if you want to get rid of some of this mess, like let's say you have all these components like this, I'll just stay on the tunnel floater example because I'm already here. You have all these components like this. You want to group it into one tiny little thing like this, you can do that in Grasshopper. So what you do, and don't follow along with this first step because I'm just going to show you sort of what you don't do before I show you what you do. But what you can do in general to make a cluster is just, select all the components you want to cluster together, like so. Right click outside of the components and click cluster. And now you can see that there are, all those big things have gone into one cluster. I'm going to go Control Z. And the reason why I said maybe that's the wrong thing to do, and it actually didn't happen, is what can happen if you're not careful about what you're clustering is you can end up with something like this. So let's try it again. So right there, you see there's no outputs. It's a dead end. Random stuff goes in, but if you look at the result, there's nothing really happening. So you don't want that. So what you need to do if you're making a cluster is you need to think about what's the input of this group of components you're going to cluster and what's the output. So what I mean is, if you look at all the things that are going into this cluster, we have our bounding boxes coming in. So the bounding boxes from the voxels, all of those are coming in, and our input text. So those are the list of all the exposed faces, the north, east, southwest, top, bottoms for each voxel. Those are the inputs of this custom cluster component we're going to make. Now, we also need to think about the outputs. So for example, if we were to cluster these, the inputs will be fine because we have two kind of inputs going in, but there's no output. So what we need to do to get the output, and this is kind of a strange thing, is we need to take the last component in this group, or the last component in this this, I don't know what you'd call it, this part of the definition that does a particular thing, and you just want to take the output and put it into another parameter. So for example, in our call pattern component, the output, we can go to parameters, we can go to, let's go to primitive and data. So data is just a component, a parameter which can take anything. So it can take text, it can take geometry, etc., etc. So let's click on parameters, primitive, data. We can plug our call pattern into the data. So that's the, in this case, tunnel floater voxels. And what we can do now is we can select everything here. So we have our two inputs, we have our output, but we don't select this final output. And what you'll find that will do when you don't select the final output, so I'm going to right click outside of it, I'm going to go cluster, is that it will give you an output that you can use in the future. So essentially we have our bounding boxes from voxels in, our input text here in. We can right click this cluster and we can call it something else. We can call it, for instance, tunnel floater voxel picker, which is the name of my prog rock band. And then you can also label the output whatever you want. So you could say tunnel floaters out. Yeah, RS.
I was just wondering, is there a way to kind of explode this in the future so we can see what we're doing?
Yes.
Or if we want to edit it?
Yep, absolutely. So once you've sort of labeled this, what you can do is you can actually just double click on it. And it's going to bring you into this this kind of new, I guess, like sub canvas. So you can see that the canvas has gone from your main Grasshopper file to a edit tunnel floater voxel picker. So now when you're in here, you're going to see there's two kind of custom components. So these first two components represent the input going into this package component. And then there's going to be one on the end. There's going to be the output right there. So you can edit all of these. You can do whatever change you want. So maybe you want to invert the Boolean, for instance, to test for an absence instead of a presence. Now you can see that you're getting different things. So it looks like, I'm not sure what you're getting. It looks like the wrong stuff, but let's say this is what we want. Once you've made that change, you can click on the little box here and you can click save and close, and that will make the change. Now, if you don't want to save and close, what you can do is you can click on the little box, go discard and close. Or sorry, you'd go to return to parent, and then that will discard it. You can then just close that right there. RS again, I think.
Sorry, I forgot to put it down.
Oh, okay, no problem. Okay, so that is kind of how you create a cluster. Now, it's kind of personal preference whether or not you use these. I know some colleagues and friends who use them extensively. If you have a computer science background, you can just think of these as like a, you know, in Python, what is a definition. So it's kind of a block of code that you can refer to. But, you know, you also don't need to use these. Maybe if you do use them in your own Grasshopper script, maybe just for my sake and Nicholas's sake when we mark them, maybe just like put cluster above and add it to a group, sort of like that, just so we know to double click on it, because, you know, when we are looking through your assignments, when we are looking through your assignments, you know, fairly quickly, we might miss that. So just make sure to list it. It's a cluster. We might not miss it, but we might. Does anyone have any questions before I move on? So what we're going to move on to now is we're going to work on box orientation. Okay, so box orientation, what do I mean? Well, we can sort of, you know, kind of figure out, I guess, what I mean by sort of giving a bad example, as it were. So I'm just going to undo this. I don't want to cluster this. You can always, oh, this is one thing I should show you. If you ever want to explode a cluster like I do right now, so I want to bring all these, this work kind of back into the main definition, I can just right click the component and go explode cluster, and that brings it back into the main definition. You can also assign a password if you want to do that, but don't do that for you know, the sake of this assignment. I won't mark something if I can't open it. And I'm gonna save this. So I've sort of saved the tunnel floater in the Grasshopper file in class. So what you'll see if you look through this file is under the corner roof section. So last class, as a class, we found all the corner roof pieces, right? Below that corner roof section, I've added in a new kind of group of components. And what these components do is they do a few things. They sort of replace the face classification with rotation angles, and then we can test to see whether or not, so testing the box orientation, we can test and see if something's going to orient properly within these boxes, and then following that we can place our blocks, which allows us to essentially place our complex geometry in here. So what I'm going to do is I'm just going to move this stuff to the side. This is sort of I guess, will act as our guide. It's sort of like you have access to my notes. The reason why I'm sharing this with you is because you'll need to reapply it to everything. So you'll need to do some figuring out outside of this in a manner similar to all the voxel classifications. So I want to show you what happens if we don't try to orient our voxels. So if you look in the notes right here, and we look at our voxel classifications, what you'll notice is I've added a fifth column which says block orientation compass. So I put in blue so it kind of stands out. And essentially what these are is they're just very simple meshes that I've made. You could also recreate these into something that works a little better for yourself. And you can use these blocks or these meshes as essentially, I guess, barometers of how your voxel is oriented, to see the orientation of voxel. Because since all these voxels are square in plan, it's kind of hard to tell which way they're actually facing, as it were. I made this blue geometry to be essentially square in plan. So the extents in the, if we consider this the x direction, are the same as the extents in the y direction. The extents in the x direction are the same as they are in the y direction, and same with these ones as well. So they're going to fit nicely into a bounding box. So what we can do, just to see what we're sort of working towards, is I want you to go to the corner roof example here, and I want you to look at the call pattern that's coming out of it, right? So let's look and see what's coming out of the call pattern in the corner roof section of this definition. You can see that it's giving us all the corner roof voxels, right? What we're going to do is we're going to place this geometry in all of those voxels and see what happens. So first, let's reference this mesh here. So let's go to params geometry mesh. We can set one mesh by right-clicking this parameter, going set one mesh. I'll right-click this and I'll just call this corner geometry test, because this is just kind of an example. So let's go corner geometry test. And what we're going to do is simply we're going to make a bounding box around it. So we're going to go transform, Euclidean, or actually, sorry, we're going to go surface, primitive, bounding box. We're going to take our corner geometry, so that's this corner geometry there. We're going to plug it into the content input of the bounding box component. And then what we're going to do is we're going to box morph it. So we're going to go transform, we're going to go Euclidean, nope, we're going to go transform, morph, box morph. So transform, morph, box morph. And what we're going to do is we are going to take our corner geometry test, our input parameter, plug into the geometry input of box morph. We're going to take our bounding box that's bounding around our corner geometry, plug into reference. And we are going to take our call pattern, so the list of all the blocks that's coming out of our corner roof group, and we're going to plug into target. So what this is going to do is it's going to take this corner geometry, it's going to put a bounding box around it, and then it's going to project this geometry from its original bounding box to all of our corner roof voxels. So let's select this box morph to see what we get. What I'm also going to do is I'm going to turn off the geometry, so the TG FSR voxels 9.5 FSR. I'm just going to turn that off so we can see it a little bit better. Maybe what I'm also going to do, because we have a lot of like random geometry showing up, is I'm going to just maybe preview off a lot of stuff, so I'm just selecting a lot of this and going preview off. Sometimes I like to do this when I'm working in Grasshopper when there's too many things turned on. So I'm pretty much selecting everything and previewing off. And then let's turn back on what we want. So what we probably want on is our original piles of voxels. So our voxel input, the very top left component, just to show us what we're working with. So there's our voxel input. And then we want to zoom back down to our corner roof section in this grid and preview back on the box morph so we can kind of see what's going on. Now, if we look and see what's going on, what you'll see is that our corners are not properly aligned, right? So what do I mean by that? If we look in maybe the top view, becomes a little bit more apparent. Our corners are all in the same orientation. So it doesn't matter whether a corner should be rotated, in this case, let's say 90 degrees clockwise to sort of describe this corner right here. Maybe I will turn back on my voxels like this. So yeah, you can see it a little bit better here. So this corner piece, it does not adequately describe the corner because it's not rotated. This corner piece here does not adequately describe this corner here because it's rotated, and so on and so forth. So all these corners need to be rotated. So when I talk about rotating the voxels, this is what I mean. We want to figure out a way to rotate these pieces so they sit in the proper orientation. So how we're going to do that is we're going to use the same kind of list of northeast, southwest, top, bottom. I'm just going to delete this corner geometry. I'm going to delete the box morph. I'm going to delete the bounding box because we don't really need it, but I'll keep this corner geometry test there just because we'll still reference this. So what we're going to do is we're going to take the northeast, southwest lists that are attached to all these voxels, and we're going to use that to determine their orientation as well as their position. So does anyone have any questions about what the objective is here? What I mean when I'm talking about voxel orientation, is that kind of clear? Okay, so sounds good. So we'll move forward. I'm just going to refer to the notes that are here, and okay, so let's look at what we have here. The first thing we want to do is we just want to reference the text. So if we look at our input text here, what I'm going to do is I'm just going to copy this component here. So I have input text, and I'll grab it and I'll type Control-C, Control-V, and what this is it's simply the text that's coming out of all the voxels. So this isn't even the called text. This is literally the text that is just coming out of, you know, the end right here. So it's kind of the raw data coming out of all the true-false conversions. So it's describing all the voxels. Since we have this true-false text coming out, the second, I'm just going to disconnect this because it's looking kind of messy and it's kind of hard to see. So I'm just going to disconnect that. So what we have here is we have our gate and. So this is the result coming out of our test for the corner roof, right? So this is leading into the call pattern component. This is the component that allows us to choose our corner roof pieces. So if we look at what's coming out here, just to review, we can go to params input panel and take our gate and out. And pretty much what this is doing is it's telling you whether or not a certain voxel is a corner roof condition. And we're using that pattern to call the pile of voxels. We're also going to use it to call the list of northeast, southwest, top, bottom. So if we look at what's coming out here, we have all these northeast, southwest, top, bottoms. We don't care about the ones that don't correspond to a corner roof condition, right? We don't care about the ones that are, you know, in the bottom here or this floater. We don't care about those. We only care about the corner roof. So we're going to do a similar thing. We're going to call all the lists we don't want. So to do that, what I'll do, I'll just leave that there, is I'll go to sets, sequence, call pattern. I'll take my input text here, so all these lists, I'll plug into the list input, and then I'll take all my outputs from my gate and I'll plug it into the call pattern. Now, what you're going to see happen here, I'll grab a panel to demonstrate, so params input panel. What you'll see here is you'll see a bunch of empty lists. And essentially what's going on is, since we're matching this data on a list for a list level, or you can think of it as a branch per branch level, this false, so the false in the 0 list, is being applied to all the items in this 0 list. The false in this 1 list is being applied to all the items in the 1 list there. Now, if we zoom down, let's find a true. There's a true somewhere in there. What's going to happen is, if we have a true, we will get these little lists that have the original values. So these are the values of the corner roofs. Now, can anyone think, if, for example, we see that we have one corner roof and it has its east face exposed, its south face exposed, and its top face exposed, and then let's look at another one. It has its north face exposed, its west face exposed, and its top face. Another one has its south face exposed, its west face exposed, and its top face exposed. Can anyone think of how we might go and classify the orientation of these corner roof voxels by the information we have here? Could you tell me in non-grasshopper language, but just kind of standard English? So this one's a little bit more tricky, but let's consider the case of the corner roof. Our corner roofs, we know, are conditions like this, where the top face is exposed, and then there's going to be, in this case, let's say the north face is exposed and the east face is exposed. So let's look at this condition in plan. So for example, if we were to look at this block in plan, we could say that its north face is exposed and its east face is exposed, right? So those are exposed faces. We could assign it, you know, an arbitrary rotation value. We could say that all values that have their north and east face exposed are rotated 0 degrees. So 0 degree rotation. From that, what we could say is, okay, let's look at another condition. So let's say the next one in the list, if we're thinking of rotating this clockwise, is going to have the east face exposed and its south face exposed, right? Because it goes from this corner to this corner. So east and south. So that's a 90 degree rotation. So we could say, okay, if this is the condition that happens, what we could do is we could assign it a 90 degree rotation. Now, what's going to happen is these, remember, are bounding boxes. So when we have a geometry that is, let's say, this little happy face that represents our corner condition, and it's aligned to another coordinate system where north is up and east is this direction, if it gets put into this box, it's only going to be rotated 0 degrees, so it's not going to rotate at all, so it'll end up like this. But if it gets put into the east-south configuration, so if it says east-south in this list, then Grasshopper will rotate it 90 degrees, so it'll end up like this. So that's how we're going to approach this. We're going to use the southwest, for instance. So let's look at southwest. What would that mean? So southwest, let's start over here. So southwest is never eat soggy southwest. If we're saying that the northeast is our 0 condition, to get to southwest we have to rotate 90 degrees, 180 degrees. So we would say that in this list, if you see a southwest, you can rotate 80 degrees. So that's the logic behind what we're going to do. So what we can do is we can just start to replace things. So I'm just going to refer to the notes here. So we want to choose the relevant faces. So in that example I was just talking about, we are always considering southwest. We're kind of forgetting about top, because if you think about it, all these corner roofs, it doesn't matter. Like, all of them have their top face exposed. So the third item in this list doesn't really matter. So what we can do is we can essentially grab the first 2 items in the list. So we can go to sets, list, list item. Our list that we want are going to be our call pattern. If we look at the output of our call pattern, you can see it's a bunch of nulls and then, you know, a south and north every once in a while. Now think about this. We want the first 2 items in this list. So what that means is, for example, if we zoom down to the list where there's actually some data, 0 is going to be the first item in the list. If we look at our list item component, the index by default is set to 0. If we zoom in on the list item, press the little plus button, we get +1. So what this means is its index equals 0. So I equals 0, +1 equals 1. If we look at our list, 1, that's west. So what we're saying is grab item 0, south, item 1, west. So now simply what we can do is we can join these together. So we're going to join them as text. Yeah, that's what we're going to do. So to do that, simply we'll go to sets, text, text join. So join a collection of text fragments into one. The text we're going to plug in are both of these. So plug in I, hold shift to plug in the +1. Since these are sorted, or these are grafted, so this data is being considered at a list or branch level, we don't have to worry about, you know, things joining that we don't care about. And if we look at the result of this, you can see that we get a bunch of empties, but then we also every once in a while get a northwest, or, you know, let's say a southwest, etc., etc. What we can do now is we can flatten this list. Actually, let's not flatten it yet. We're going to do one more thing. So if you think back to that example I gave you, right? So we're saying if our kind of base condition is, let's say, a north. In this example, our base condition is a northeast, right? And we say that's 0 degree rotation. From here, we could say that a southeast, or we could say in this kind of, you know, grasshopper speak, east-south would be a 90 degree rotation. So what we are going to start to do now is we're going to start to replace these face classification, so north and east, with a rotation. So what I mean by that is let's type in the different rotations of faces we can have. So let's go to params, panel. We'll grab 2 panels. We'll go params, panel again. We're going to have more than one item in each of these panels. So let's right-click one, click on multi-line data. Right-click the other one, click on multi-line data. Remember, that allows you to have lists. We'll right-click the first panel and call it exposed faces to replace. And we'll right-click the second one, and we'll call this maybe degrees to, or let's call it rotations to replace with. And what we're going to do is let's just start from northeast, because it's kind of the first that comes in the list, you know. Again, like I said, never eat soggy wieners. Learned in Cub Scouts a long time ago. So let's put in northeast. So the first item this list will be NE. I'm sticking with uppercase letters. Enter to put a second item this list. The next item this list, if we think about rotating around, would be east-south. Following east-south, we can think of southwest. And then finally, and this might be a little bit counterintuitive, but I'll explain this in a moment, we're going to go northwest. So that's kind of the only one that breaks the rule. So we're going to go northwest. So northeast, east-south, southwest, northwest. And the reason why we go northwest is if you think about what we had before, is we have this list of northeast, southwest like this. And if we're joining the exposed faces, it's always going to join in the order of this list. So in this case, the first one is going to join is northeast. Following northeast, it's going to join east-south, so east-south. Following east-south, it's going to join southwest. And then even though, you know, if we're thinking of northeast, southwest, you'd think, well, if we're going to rotate this way, we would end up at west-north. But since this list has north coming first, we'd go 0, joins with list item 3, gives us northwest. So that's why we go northeast, east-south, southwest, northwest. We want to replace these with degrees, so rotations to replace with. And let's go 0, 90, 180, 270. And I'd say to start out with 0, 90, 180, 270. So rotating in 90-degree increments. And we're going to switch these around because everyone might have different rotations. This is something that you're going to need to figure out by yourself. And right now I'm going to show you how to figure it out. So what we can do is we can replace these with these. So to do that, what we're going to do is we're going to go to sets, replace members. So sets, replace members. The set we're going to operate on is our text join output. The find, so items to replace, are going to be the exposed faces to replace. And the rotations to replace with are going to go into the replace. What we're going to find, I'll just look at the output. So I'll grab a panel, look at the output. Is that, again, we have all these empty lists because a lot of these coordinates have been called, but we will get some rotations. What we can do at the end of this replace members is we can right click on the result output and click flatten. And that should have gone rid of the empties. I thought it was going to get rid of the empties. What we can do instead, perhaps, is try flattening on the set input. Let's try flattening on the text join output. Bizarre. Where did I flatten here? Yeah, I did flatten there. What the hell? Clean tree? Yeah, Bryn, that's a good idea. So essentially what I want to do here is by flattening this replace members output, what I was hoping to do is a lot of times when you flatten a list, it's just going to get rid of the empties like that. Sometimes Grasshopper is kind of strange, and because of that, you know, strangeness, sometimes it's not doing what I thought it was going to do. So it's not getting rid of these empties. So instead, what we can do is suggest in the chat, and thank you so much for your helpful suggestion, is we're going to use a component called clean tree. So we'll go to params, sets, tree, and then clean tree. So clean tree is the little hacksaw there. And you can see what clean tree does is it removes nulls, it removes invalids, and it also removes empty branches if you click this value to be true. By default, it's false. So let's right click the remove empty, go to set Boolean, set it to be true. And now we can plug in our replace members. So make sure it's not flattened, plug into the tree, and then now we can flatten it. And man, oh man, there's something going on that's weird here. So we might want to do this before. So sometimes, I don't know why it's doing this. Is this working for anyone else? Toggle true, remove empty. Yeah, remove empty is true. Is it just my computer that's having this issue? Because it really shouldn't be. Can anyone else confirm that what they're getting is just a list that doesn't have all these empties? Mine is too. Okay, so it's something we can solve together. So essentially what's going on here is we just need to remove the empties at some point in our definition. So maybe what we'll do is let's just disconnect our clean tree component, and let's plug it so we have this call pattern. And this is where we first see these horrible empty branches, right? So the call pattern has these kind of collapsed branches like that. Let's take this call pattern, plug into tree, and there we go. So that works. So essentially what that's going to do is it's just going to get rid of our empty branches at this stage. You can see an interesting thing is worth pointing out is it retains the paths numbers of the branches. So even though you know, there's no branches before it because branches 0 to 93 are empty, it still retains its number. So that's number 94. So we can take this clean tree result, let's plug this into the list item. And now when we look at the replace members output, you can see that we don't have all these empty branches, and we can flatten the output. So that's kind of what you should see. And an interesting thing to point out is that you can see it says locally defined values. We have 28 of them, so 28 locally defined values. If you hover over the call pattern coming out of your corner roof definition, you'll see that there's 28 voxels, so the same amount as we have rotations. So what that means is we've now defined one rotation per voxel. So that's what we want to see. Now that we've done all this, and we've sort of gone rid of the empty trees, why don't we go back and group this? So it gives us a chance to review what we've done, and it will also allow us to kind of tidy this up. So the first part of this, essentially we took trues and false from our gate and. So maybe what we can do here is we can I'm going to clean this up. I'm going to replace this panel with a Boolean because we don't really need to see this. So what I'll do is I'll go params primitive Boolean. I'll right click this Boolean, and when I'm going to reuse a definition like this, I like kind of labeling it like input goes here, you know, like a direction. So maybe I'll call this calling pattern in here. Calling pattern input. Yeah, I'll call it calling pattern input. The calling pattern input will be the result, and I'll plug that into my call pattern. So I'm just replacing this panel there. My input text, I can get rid of this panel. I just kind of use this as an example. And I will group this, I'll group the inputs as well as up to the clean tree. So essentially what's going on here is we input our text, we input our call pattern. So I'll call this group calling list of exposed faces and removing empty branches with clean tree. So that's what we're doing there. The next thing we have here is we're choosing the side faces. So if you remember, what's coming out of the clean tree is the northwest top or the southwest top. We don't need the top, so we're just choosing the first two items in the list. We're joining it, and we're replacing the values. So maybe it makes sense to group the list item and the text join. That group there, we can join this, and we can say choosing the faces we need. I'll even elaborate and say the side faces we need to determine orientation. And then finally, we can group this replace members section, and I'll call this replacing exposed faces with rotations, like so. So does that make sense to everyone? Okay, so what I am going to do is I'm now going to sort of test out the rotation. So we want to see the rotations, and we might need to kind of mess around with these rotations to replace with in order to properly suit the pile of voxels we have at hand. So what we're going to do is we have this corner geometry test, this reference corner geometry, and you know what? I'll just re-reference it so everyone's on the same page. So what I'm going to do is I just want to go to my little column of block orientation compasses, and I want to find the corner. So that's this one right here. I'm going to reference it. So I'm going to go to params, geometry, mesh. So all these block orientation compasses are meshes. I'm going to right click the mesh, going to go set one mesh. And then maybe I'll rename this. I'll rename it block orientation compass. And now what I'm going to do is I'm going to place it in rotated voxels. So before I place, I need to rotate these voxels, and this is pretty easy to do. So we have our list of called voxels, right? So in this case, we have all our corner roofs. Let's just put them into a parameter like we've done here, because we're going to reuse this chunk of script quite a bit. So we know that these are boxes. So what we'll do is we'll go to params, geometry, box. We'll take the call pattern, plug into the box. I'll right click this box parameter. I'll call it voxel boxes input. So I have a nice description. And now what we want to do, I'll just drag it. Actually, maybe I'll just leave it at the front of this kind of chunk of code. I'm just getting kind of cramped here, so I'll move that big group. What I'm going to do is I'm going to take these voxels and I'm going to rotate them by the amount specified here. So I don't want to rotate them around the XY axis, because what's going to happen, we can try doing it. Let's go to transform, Euclidean, rotate. So transform, Euclidean, rotate. The geometry we want to rotate is our voxels. So I plug that into geometry. You can see they're flying out here. The angle we want to rotate them by is this replace members. Now remember that by default angles in Grasshopper are defined in radians. We want to define them in degrees. So you can right click the angle input and turn on the degree conversion. So now that'll rotate these pieces in degrees. Now you can see here that what's happening is they're rotating around the center point of our Rhino model, and that's why they're kind of flying out into the distance. So what we need to do is we need to define a local plane for each voxel. The easiest way to do that for each voxel is just to take its center point. So simply what we can do, I'll just move the block orientation compass up there. We can go to surface, analysis, and then box properties. So get some properties of a box. And we can take our voxel boxes input parameter. So in this case, our corner roofs, plug into the box input, and that's going to give us a bunch of center points. So now let's plug our center points into our planes. And now you can see they're not flying off into space. Now, it might look like nothing's happened here, but if you think about it, if you rotate a square 90 degrees, a square has, you know, it's of equal dimension in both the X and Y axes, it's going to look the same if you rotate it 90, 180, 270, or 360. So that's why these don't look like they've moved, but let me assure you that they have. Now what we can do is we can do a little test. Maybe what we'll do right now before we do said test is let's take this box properties and the rotate, and let's just add it to this group right here. So add to group, and that's just adding it to the replace members. So rotate component says data conversion failed from text to number. So probably what that means is that you have some sort of error in your find or in your rotation. So I think what's probably going on here is you might have pressed enter after your last northwest, for instance, put an empty, and then that's giving you some sort of you know, error. That could be something that happens. If not, we can kind of figure it out during the break, which will be shortly. So what we're going to do now is we will take these block orientation compass, or we'll take it and we'll place in these boxes. So we're going to create a bounding box around it like we did at the beginning of class. So it's this one right here. We'll go to surface, primitive bounding box. The block orientation compass I'll plug into the content input of the bounding box. There it is. And then what I'm going to do is I'm going to go to transform, Euclidean, transform, morph, box morph. So this is the same as we did earlier in the class, except this time it's going to work. So this geometry, the block orientation compass, will plug into geometry. That's the geometry we want to move. The reference box will be this reference box. And the target will be all our rotated voxel boxes. Once we've done that, I'm just going to group this before looking at the results. So I'm going to group these 3 components. I'll right click the group and I'll just call it orientation test, because this isn't our final geometry. This is just something that allows us to tweak it before committing to our final geometry, because as you'll see, there is sort of a point where we switch from grasshopper to rhino, and at that point it's not impossible at all, but I mean, as far as, you know, flexible parametric design goes, it's kind of clunky, so it's good to test first. So let's look and see what the test is giving us. Okay, so if I turn on my voxels again, because that seems to be a good way to see everything, it looks pretty good at first. So look at this, our corner piece, you can see the green right there, it's in the right orientation. This one's in the right orientation as well. That is not in the right orientation. That's in the right orientation. So essentially what it looks like is that we have some of these rotations correct, but some of them are incorrect. So if you get a condition like this, don't worry. That's why we're doing this test. Essentially what it means is you just need to flip around some of your replacements. So in this case, if I remember right from kind of working through this file the other day, we need to switch out, I believe, the 0 and 180. So essentially the northeast and southwest need to be replaced. So let's try this. Let's double click on our rotations to replace with, swap our 180, put our 180 in the first spot. So northeast is going to be swapped with 180. Southwest is going to be swapped with 0. Click out. Click our box morph again. And now that looks correct. That condition looks correct. That condition looks correct. That condition looks correct. That's correct. So this is great. Essentially what's going on, we can preview off this stuff, is we have all these, you know, properly aligned corner pieces. You can see that this kind of properly describes the pile of voxels. So does that make sense to you guys? We're going to take a break right away. And after that, what we're going to do is we're going to actually start assigning detailed geometry into these orientations. And then following that, it's not going to be a ton of time, but maybe for about 45 minutes, half an hour, we'll break out into groups again to let you guys maybe try a couple of the different classifications. So, and I'll try to answer some questions at break. So Meredith, though, is saying, mine are showing our 4-sided frames, but I use the L-shaped corner piece. Jeremy, okay, so Meredith, I'll answer this question first. We're showing our 4-sided frames, but I use the L-shaped corner piece. It could be that you're plugging your box into your geometry like that. So blocky orientation compass needs to go into geometry. So that could be your issue. RS, I'll answer your question because it's quick. If you go to the assignment sheet, so under syllabus assignments on assignment 2, there is a submission link right there. So you can just follow this link and it's going to take you to the same Dropbox submission form. Meredith, let me know if that solves your problem, if that was it. If not, we can talk over break. Okay, Meredith, we'll take a break and then I'll tackle yours. So, okay, so let's okay, so why don't we tackle a few problems? So Meredith, could you send me your Grasshopper and Rhino file? Ellen, can you send me your Grasshopper and Rhino file? Jeremy, let me know if G-Ling's fix worked. And rather than that, we're going to take a 10-minute break. So I'll try to tackle those issues during the break. And I'm just going to, I'll be back in a moment, and I'll go through those. So whoever's email I get first, I'll just tackle first. So stay online, and I'll be back right away. Thanks. So what we're going to do now is we're going to preview off. Actually, we can leave preview on. Doesn't really matter. What we're going to do now is we are going to start placing blocks. So we're going to use the instance manager component again. And if you remember, this is the one we use to place trees. You should still have it installed. If for some reason you uninstalled it, the link's in the syllabus. So what we're going to do is we're going to go to the Heteroptera or Heteroptera tab. We're going to go to Instance Manager, and we are going to go to Insert Block by Box. So Insert Block by Box. So if you remember what this definition does is it takes boxes like we have here, inserts a block into them. So let's see what this component needs. So this component, if we hover over it, first it needs a definition, so an instance reference definition. So what does that mean? That simply means a block. What we need to do is we need to create a block in Rhino. So we're going to create a block for each one of these conditions, and these are going to be kind of stand-ins for the complex geometry we're going to put into those voxels. So you can see what I've done here is I have these kind of pink, these magenta voxel stand-ins. And the reason why I've made these pink magenta voxel stand-ins is because I don't want to deal with complex scaling. What I'm going to do is I'm going to put in a stand-in into a block. I'm going to place it in this pile, and then afterwards I'm going to edit the block and place the complex geometry into it. So when I was putting together this course, I tried it a few different ways. I tried just placing this complex geometry into the voxel pile. I tried scaling it, then placing it. And the thing that worked easiest was just to place a very simple kind of placeholder block into a voxel, and then afterwards in Rhino replace it. So if that's not totally clear what I mean right now, that's a-okay. I'm going to show you what I mean. So what I would do if I was starting from scratch, so let's pretend that I don't have this beautiful corner roof piece. I deleted that kind of magenta bounding box. What I would do is I would go to my tower of voxels, and I would choose a representative voxel. So I'm just going to minimize Grasshopper right now. I would choose, for instance, this voxel right here. Now, you will have voxels probably towards the bottom that are taller, and this definition will proportionately stretch your blocks, so you don't have to worry about the fact if you have different heights of voxels. Just choose the height that you have the most of. So in my case, you know, it's towards the top. Yours will probably be towards the top as well. Just to keep things order, I'd work with the template file. You know, copy your own custom geometry into this template, and what I'd do is I'd just go transform, copy, selecting one voxel, and I would just copy a standard voxel into the kind of cell in this legend that you want to work with. You can see this voxel is on an angle. I would select this voxel, and I'd go transform rotate, and then I would just rotate it, so I'm holding shift now to snap it to the kind of ortho, so snap it to the x-axis, and there we go. I have my voxel, right? Now, if you were going to do this, you could like go ahead and use these pink voxels if they work for you. But if you want something that's closer to your own, you know, voxel, you can do that too. Probably the pink voxels work for you. If you wanted to, what you could do is you could then copy this voxel to all these grids, so you sort of have a template. What you might also choose to do is, you know, change the layer. So maybe I'm going to change this layer to the, in this case, it is the corner roof layer. So I'm selecting the corner roof layer that's in the template, the site file. I'm going to right click, go change object layer. And then what I like doing to make sure this is a guide, because this is going to be something we build within, is I'm actually just going to change the visibility of this voxel, as it were. So what I'm going to do is I'm going to go to my Properties tab. I'm going to go to Display Color, and I'm going to go to Magenta. It's just a bright color that stands out. So again, select the object, go to Properties, go to Display Color, Magenta. And then you'll notice that all these other kind of boxes here, they are essentially, you can see they're transparent, right? It says it's an extrusion, however, you can see through it. And the way you can do that is you can select an object, and you can use the command object display properties. So start typing in object display, or it's set object display mode. That's the command. So set object display mode, hit enter. And then now what you can do is you can click on the mode and then set it to wireframe. And now you can see what happens is I just have a wireframe of that mesh. So this is kind of my stand-in. Now, what you're going to do, and we'll spend next class sort of discussing how you can go about designing your own components, and maybe you want to get a jump start on it over the weekend if you're really excited to do this, is we are going to, let's say, start building within this voxel. So for right now, we can use the example file, but next week we are going to start building geometry. What I'm going to do is I'm just going to simply, for right now, place it at the corners of this kind of bounding voxel. So you can see what I did with my geometry is, you know, I more or less fit into this box, right? I made sure that all the interior faces lined up with this box so that when it connects with other voxels, it joins them. And then I thought about, you know, the other pieces in this system, but we'll get into that next week. What's important at this point is you have your sort of representative initial voxel that you're going to use to create a block. So once you have that done, so you have this kind of representative placeholder block made, we can create a block from it. So if you remember, we created blocks from the trees, and what a block is, just quickly to refresh, you don't have to follow along with this, is it's simply an object that can be duplicated, and it retains the same information in all the blocks. So for example, let's say I create this item that has these two cylinders. If I were to type the command block, pick a base point, give it a name, so I'll call it 2 columns. 2 columns. What would happen is if I copied this block and then edited it by, you know, double clicking on it. So you double click on a block, it edits it, and then I make a transformation to it. Let's say I rotate this column here, click OK. All instances of that block will update. So that's why what we're going to do is we're going to make this a block, place it all throughout this pile of voxels, and then after it's placed, we'll add this complex geometry to this block, and it'll update all over the file. So what we're going to do is we are going to create a block. So we're going to create a block that's called corner roof. And now I'm going to ask you to do something that I wouldn't normally ask you to do if you're working in your own file, but I'm going to ask you to do this in anticipation of future problems that might arise when I try to essentially collate all the towers into one big virtual city, which will be really interesting. Is I want you to append maybe your first initial and last name to this block name, just so when I put all the files together, we don't have a million corner roof blocks. Instead, we have in my case, corner roof T Godden. So what I'm going to do is I'm going to select this placeholder block. I'm going to type block. So block. I'm going to choose a base point. Just choose one of the corners. It doesn't really matter. Maybe the bottom left-hand corner. That kind of intuitively makes sense. And then I'm going to call this corner, let's say corner roof underscore T Godden. I'll click OK. And that's my block there. So this block, you can see when I select it now under its properties tab, it says corner roof T Godden block instance. So does anyone have any questions about that, about the creation of the blocks? Okay. So what we're going to do is we're going to go back into Grasshopper. And if you remember, we're working with this instance manager component. So insert block by box. So that's in the Heteroptera tab under the instance manager subtab. The first thing we need, instance reference definition. This just means the block. So let's go to parameters, primitive, and then go block definition. So block definition. What we'll do is we'll right click this and we'll go set one Rhino block. And we'll click on the Rhino block we just made. And you can see that if we hover over the block definition, it says corner roof underscore T Godden. So please name your blocks in this kind of, with this kind of nomenclature. The block definition, we can plug into definition. The transform block is the blocks we want to put it in. So in this case, it is our box morph, or it's not our box morph geometry, sorry. It's our rotated boxes. So if you remember, we replaced the members, we found our bounding box centers, and then we rotated the bounding boxes. So we want to take the geometry output from our rotate component, place into transform box. The third input is place, which needs a Boolean toggle. So let's grab one. Let's go to parameters, input, Boolean toggle. And the last thing we want to do is we want to define a layer, because we want to keep our file kind of neat and organized. And I think some people kind of found with their trees that they might have sort of lost where their trees were. It essentially baked onto the wrong layer. So what we can do is, you can see that right here, because I have this like corner roof piled kind of demonstration component down here, essentially what's going on is that it's creating a new layer. So what you can do with Heteroptera is you can go to Heteroptera, you can go to Instance Manager, you can go to Attribute Build, and essentially you can define a layer right in Grasshopper. So you can go to Parameters, Input, Panel, put it on the canvas. Let's right click this panel, call it Block Layer. And then let's just create a new layer and call it Corner Roof Placed. Maybe that's what we call it, just to make sure that it's placed. Let's plug that into layer. And you can see as soon as I plug into layer, I have a new corner roof placed layer. Another thing that I'm going to try right now, I don't know if it'll work or not. Let's see if this works. If it doesn't, I won't say what I was trying to do. Nope, doesn't work. Okay, that's fine. So essentially, you're just going to, you know, make a layer that you want to place your block on, and you can organize it afterwards. So let's make a corner roof placed. I'll delete these kind of extra layers that are there. And I'll plug this attribute into my attribute input, insert block by box. Once that's all hooked up, what I can do is I can double click the Boolean toggle, go true. You can see it's placed my box in my tower. I'll double click to turn this off because I don't want this to keep updating. Now, after this, what I can do is I can actually just close Grasshopper because I'm done using Grasshopper for the moment. What you're going to see is you have all these block instances placed in your tower. And right now it might not look like much because it's a placeholder, right? So if we click on the block instance, let's say right there, you'll see that it says one block instance added to selection up there. And in its properties, it says corner, roof, T-Garden, block instance. So that's good. That's what we want. What we can do is we can go back to our legend here and we can start editing this block. So corner, roof. Let's zoom in. So I'm going to go view, zoom, selected. What I can do is I can select the block, so make sure one block instance added to selection, and you can either double click it, or if it's hard to double click it, you can select it and go block edit, and that's just going to bring up the block edit mode. So you'll know you're in block edit mode when everything else is kind of grayed out. You see, like everything else you can't really select it, you're just editing this one block. Now this block right now simply has one item in it. And what we can do, we want to take this placeholder out. We'll select the placeholder, we'll click on remove object, and then we'll go to add object, and we'll add our detailed geometry, like so. We'll press enter. Oops, I accidentally added that again. So again, select your placeholder, go remove object. And now you can see my block, it has my complex geometry. I've removed the placeholder, so once that's done, just click OK. Now, you're going to find something kind of strange. So when you add an object to a block, it creates a duplicate. So for instance, you'll see that if I click on this little Tom Nook gargoyle there, it says mesh, but then behind is the block instance. So you probably want to delete the duplicate. So what you can do is you can just turn off mesh in your selection filter. So if you don't have your selection filter up there, I'll reset it up to show you because it's super useful, and everyone who uses Rhino should have their selection filter. So to use your selection filter, just go to edit and then selection filter. This little tab's going to pop up, and for all of you, I think you should probably just take this selection filter, and I like putting it above my tabs. So now you can see I have this selection filter up there, and what that allows you to do is, you know, essentially, for instance, if I deselect the blocks, so I uncheck the blocks category, now what I can do is I can select this, and you can see it's going to select everything but my block, and I can just click delete. Now I might not want to delete my reference, pink reference box I made, because this might just be a nice useful guide, right? It sort of shows me the extents of my voxel and sort of the relationship of my geometry to my original voxel. But I am going to select the detailed mesh geometry that's a duplicate now, and I'll just click delete. And now what you'll see is I still have the block left as the detailed geometry, and I have my reference voxel there. I can turn back on my block selection, and now you can see I can again start editing my block. So that's great. Let's go look at what happened in our tower. You can see what's happened is wherever there was that condition, we have placed this block. So you can see that right now it's overlapping with my kind of TGE FSR voxel tower, kind of the blank massing. But what's going to happen is you go through this process and you start building it up. Once you eventually just turn off your essentially assignment 2 geometry, you are going to have a beautiful, maybe strange, maybe highly modernist, maybe traditional, who knows, but you're going to have a highly complex, but actually not too computationally heavy, because we're going to deal with creating very simple geometry next class. You're going to create this kind of stunningly complex thing. Now, one really nice thing about using blocks in this situation is once you place them, you can go and edit them. So for instance, let's say I'm really don't like this gargoyle here, right? I want to replace it with something else. So what I can do, so you might get this kind of warning there, that's fine. You can go back to your original block here. So let's zoom back into our corner and double click on it to edit our block. So I'm just going to go view, zoom, selected. And let's say instead of all of Tom Nook, I just want, ooh, maybe I shouldn't have exploded him like that. That's fine. I just want his head. Oh, apparently most of the detail in this Tom Nook model is in his shirt print. That is so odd. So yeah, let's say I just want his head. So I'm just going to sink his body into this pedestal there. Right? So he's just saying like that. That's what I want. So once I'm happy with that, I can just click OK. And then what you'll find is that you go back to your building and all of the corner conditions have updated. Now, one thing you can always do is, let's say you want a unique condition, like let's say this corner is a special corner and you want to put special program there. You can just go explode block, and now all of a sudden this is a unique corner and it won't affect all the other blocks. So that's kind of how we place blocks. I'll also say, to answer, so RS, these towers are going to look hectic soon. Yeah, they absolutely could be. Refer back to the Mark Foster Gage image. But I will actually leave it up to you guys if you want to insert big masses of plane geometry. So for the final project, you don't have to have this aggregation of, you know, all these pieces. You can mix and match and model in different Rhino pieces you want, maybe to introduce some moments of calm. So that is where I will leave it for today. What we're going to do next class is we're going to talk about how to essentially go about modeling these sections. So I want to show you some tips for modeling things that are very geometrically light, because in this situation you're gaining a lot of complexity on sort of a macro scale. So on the micro component scale, we actually want these pieces to be quite simple. We'll reintroduce a lot of visual richness later on when we render them and we play around with textures. But as far as like geometry is concerned, we want to use what video game designers call low poly geometry. So we don't want it to be particularly complex. So maybe I'll just bring up Grasshopper. So again, in the file I saved in class today, it's going to have this definition here, which essentially does what I did there. But it is all of your responsibility now, sometime between now and essentially the hand-in for assignment 3. I want you, between either yourself or the group you met with last class, to go through, figure out the classifications like we did last class for all these conditions. Maybe you've done most of them already. And then afterwards, assign blocks to all those conditions in your tower, so that moving forward we can start working on the fun part of just modeling stuff into these conditions. So that's where the rest of the course is going to progress. So we're going to fill these towers, we're going to, render them, and then we're going to hopefully walk through them in a city. So even for next week on Monday, I'm going to prepare everyone's assignment 2s, put them on the island so we can kind of look at them. So I'm going to send out a walkthrough file to all of you to kind of peruse this coming up week. So it should be fun seeing everyone's towers together. So I'll stick around for a bit for questions, but that's the end of the class for today. So feel free to send me emails if you have any questions. I will say that for assignment 2, I know that there are a few of your questions that maybe have not been answered. I'm trying to stay on top of them, but unfortunately right now I also have a huge deadline in my professional work for Friday, a big Class B costing submission, which is about as fun as it sounds. So I won't have a ton of time to answer questions between now and Friday. That being said, if you're super stuck on assignment 2 and just something won't open, just send me an email and I can get back to your questions over the weekend. And if that's the case, I am fine with you just handing in your assignment at the end of the weekend after I ask your question. But I've seen a lot of you have already handed in assignment 2, so that's great. If you can do it, please do it. So thank you very much, and I'll stick around for a bit for some questions, but rather than that, I'll see you on Monday. Okay, thank you. Yeah, Jeremy.